In this video, I'm going to talk about pendulums and mass springs in terms of simple harmonic motion and how to calculate with them. Please read the success criteria I plan to cover in this lesson. Notice the equations that I will be using. So you should know that pendulums and mass spring systems are examples of simple harmonic oscillation. If you don't know what that means, you really should go watch my video, What is Simple Harmonic Motion? One of the things I point out is that angular frequency, this letter here, omega, is not just a regular frequency, but it's actually radians per second. Now in our data booklet, we have this equation here. The period, the time it takes for one oscillation, is going to be the inverse of the frequency, or you can calculate as 2 pi over this omega. To be honest, this is how I remember it. Omega, because it's the angular frequency, I need 2 pi and frequency. If you rearrange that with these two parts here, you'll see they're exactly the same. Now, why is that so important? Well, when it comes to acceleration, our acceleration is directly proportional to our displacement. The negative sign says they're in the opposite direction. And the constant here that makes this an equation rather than a proportion is going to be omega squared. Now, we also have these two other equations in our data booklet, and we need to know what they refer to. Now, this one here that has a length and the acceleration due to gravity goes with our pendulum. Notice that the mass of this pendulum actually has no effect on the period. One of the things is that the length should be measured from here to the center of mass of this bob. Very often students, when they're doing pendulum experiments, they actually only measure to the top of this mass, and therefore they tend to have a systematic error in their results. Now M and K, M being a mass and K being a spring constant, that is for our mass and spring combination. Now notice I have it both vertically and horizontally. The same equation works for both. In this case, I need to have my equilibrium here, and that will be where the spring is as it's stretched with the mass hanging down. This is not with the unstretched spring. We will let it go to equilibrium first, and then we will write where our x equals 0. For horizontal spring, we also need to have a limitation. This is going to need to be a frictionless surface, and then we don't have to worry about any kind of work against friction. Yes, it's true that friction will always oppose the motion, so we'll still get a net force that we can use, but the friction would cause energy dissipation over time, which would then decrease our amplitude. So let's go through an example. In this case, I've got a baby bouncer. Here we go. We've got a cute little kid here going to go bouncing up and down. We have a mass of 10 kilograms, and the rope stretches by 0.25 meters. So that means that when my mass is hanging, my stretched value that I'm going to use to calculate my spring constant is 0.25 meters. When there bounces, she will then move, and it tells us simple harmonic motion, so we'll assume that's true, and we're asked for the period. Now, if you remember the equation that we had for a mass spring system, and that's basically what we have, 2 pi root m over k. Before I can do anything, I'm going to need to find the k value, the spring constant. Well, we do know this. Force is equal to k times x for our spring. And yes, there's a negative sign here, saying that the force and the displacement are opposite directions. Now, when I put the baby on here and it stretches by this much, now that means that my force due to gravity, pulling down, is equal to the force from the spring. So I can calculate how much we should have for our spring constant. It'll be our mass, 10 kilograms, times 9.8 over, and notice this needs to be in meters because I've got kilograms and meters, meters per second squared. I want to be able to have my units of K in newtons per meter. If I pick up my handy dandy calculator, I get 392 newtons per meter. So I'm going to go back here to my period. I'm going to substitute my values. 10 over 392, and I get a value of 1.0 seconds. One thing I want to point out here as well is this question asked for the time period. Sometimes they'll just say period and assume you realize it's a period of time. A mass of 78 grams is suspended from a fixed point. The stationary mass is pulled down through a distance of 2.1 centimeters and then released. And we have a period of 0.69 seconds. Calculate the angular frequency. Okay, so omega is going to be 2 pi over the period. So that's fairly straightforward, and I pick up my calculator. I'm going to get 9.1 radians per second. Now it asks me to calculate the spring constant. Let's use our equation. The period, 2 pi mass over the spring constant. Let me bring the 2 pi over to the side. T is going to be over 2 pi. Now that would equal root m over k. Don't like the root sign, so let me square all of this. M over k. Running out of some room here. Now I'm looking for k, so I'm going to cross multiply my pieces here. K is going to equal 2 pi squared, which will be 4 pi squared times m over t squared. I'll put some numbers in. Notice I have to put this into kilograms because I want my units to have newtons in them, and hidden inside newtons are kilograms, meters, and seconds. And picking up my handy dandy calculator, I've got 6.5 newtons per meter. Example 3. I have a motion sensor here, and it made a displacement time graph for my pendulum. So this is how I could set it up. If I have the top of my pendulum here, my bob, and it's going to swing back and forth, and by placing my motion detector over here, it's going to measure something coming towards it and away from it. So this positive could be, for example, towards, and this could be away. And I could get a graph that looks like this. Now it says, from the graph, determine the amplitude. Remember that would be from here and down to here. The symbol for amplitude in subharmonic motion is x naught, and that would equal 0.4 meters. Don't forget to read the labels in case there's any multipliers. And the period, now if I start here, one whole period would go to here. Some people would like to say, oh, that's a wavelength, but technically, since it's time on the x-axis, a wavelength would be measured in meters. This is a period, the time it takes for one oscillation. And we could go from here to here, but to be honest, it's not quite perfect, and the IB is going to assume that you're going to measure to the nearest half square. So I would suggest you go 1, 2, 3, and measure this one over here as well. Now, when I do that, the first peak, I see that at 1.2, and second, third, fourth peak is at 16.2. Remember, one large block here has broken down into 5 pieces. This is 2, so each small square is decimal 4. This is halfway in between, so I'm going to call it 0.2. If I do this, that means that 3 oscillations will equal 15 seconds. So that means my period must be 5.0 seconds. Part 2 says, what is the angular frequency? That's 2 pi over the period. gives me 1.26, and looking at my values, I'm going to round that to 1.3 radians per second. And then finally, B. What is the length of the string? Period is 2 pi length over G. Again, I'm going to move that around. Period over 2 pi would be root L over G. So I'm just going to get rid of the root sign and square this. My length will be T squared over 4 pi squared times G. And picking it up in my calculator, I get 6.2 meters. Now you might be going, oh my goodness, really? 6-meter pendulum? Does that make sense? Well, if you think about a grandfather clock and they have a pendulum going back and forth, they're usually around a second. And the grandfather clock is usually up to 1 meter long here. Longer the length, the greater the period. So it has to be longer than 1 meter. And in fact, if it takes 5 full seconds for it to swing back and forth, that will be a very long pendulum. So that's it for this video. Please read the success criteria, and hopefully you can say yes to all of these bullet points.